Okay, welcome back. We have just seen the definitions of stereoselective and stereospecific reactions and asymmetric synthesis. Okay, and in true sense they are all different, but in reality what happens, the stereoselectivity is now most often clubbed with asymmetric synthesis. So, if an asymmetric synthesis, the actual asymmetric synthesis definition, that whenever a chiral center is converted into a chiral center, and if you get one configuration in excess over the other, that is asymmetric synthesis. Many scientists call it that it is a stereoselective synthesis, that you are making one stereoisomer more over the other. Okay. Now, I will just show you a few slides to impress upon you that again upon the importance of this asymmetric synthesis, and the definitions are also included here. See, what you should know, that most of the naturally occurring compounds that we see in our daily life, most of the naturally occurring or biologically active organic compounds, they contain chiral centers, and nature makes creates these chiral centers only in one configuration with a defined geometry. And the question is, that means nature has the ability to make compounds or to make asymmetric synthesis of highest order. So, whenever we take, say, get menthol or drugs like antimalarial drugs like quinine, synconine, whatever compound you call, if they are mostly chiral, and if it is chiral, that is obtained in one enantiomeric form, and that is the beauty of nature. And you have to asymmetric synthesis is, I have given you the definition, that a chiral unit is converted into an chiral unit. So, that is one textbook definition, but I gave you that one chiral center. I have defined this unit as a chiral center, and convert a chiral center converted to a chiral center in unequal amounts, that is called an asymmetric synthesis. Now, asymmetric synthesis, why is important? I again quote some examples, that there are molecules which are artificially made, like this compound. These are called the sex pheromones, means they can attract the opposite partner. But when you take the mirror image of this molecule, this attracts males and this attracts females. So, only there is a difference in the stereochemistry. This is the mirror image of this one. So, one enantiomer, if it is present in the body, then the males feel an affinity towards the animal which is secreting this type of compound. On the other hand, females have the affinity, affinity if some animal is secreting this molecule. So, you see, just a difference in stereochemistry can have different biological activity, can discriminate between two opposite people, male and female. Similarly, there was one drug, this is a man-made drug, thalidomide. This name was thalidomide, and the structure is shown here. This was sold in the 1960s as a plus minus mixture, that means as a racemic mixture, and it was given to pregnant mothers. Okay, the pregnant mothers who are likely to have child very soon. So, those that was, now what happened, this was given as DL mixture. At that time, drugs were all given as racemic mixture unless they are naturally occurring, because natural products are all chiral. So, the synthetic drugs were usually made in the laboratory, they are all prepared in the DL form, because DL form is the easier ones to make. If you want to make it in the optically pure form, then you have to do an asymmetric synthesis, and asymmetric synthesis will cost you more, because your design has to be more subtle and more chemically intensive. So, the cost was higher if you want to have only optically pure of this or that. So, the drug companies, just to cut down their costs, they were introducing the DL pair, thinking that they will have the similar kind of effect in the body. But what happened, thalidomide was meant to have a sedative action for morning sickness, which is usually the pregnant women suffers. But what happened, this is the molecule which with this configuration that has the sedative effect. The other compound, the mirror image, causes fetal defects. That means, it is called a teratogenic compound, which causes birth defects. And what happened, the babies that were formed from mothers who were taking this thalidomide, the babies were born with deformed limbs, deformed legs, and this is one of the greatest tragedy in human history, that and that brought us to the importance of chirality, in pharmaceutical industry. I told you in the beginning that chirality is very important in pharmaceutical industry, and this was the turning moment in the history of drug industry, when drug industries realized that in order to sell a drug, you have to have a you have to first know what the effects of the plus compound and what are the effects of the minus compound. It may so happen that the plus compound is the one which is giving the required effect and the minus compound is toxic, then you have to give the drug as a chiral drug. There are many examples today of chiral drugs, like anti-ulcer drugs, S-omeprazole, like the anti-Parkinson drug that is called L-dopa, like levocetrizine is another one, an anti-allergic drug. So, there are many such drugs, which are now sold as only the in the actual active chiral form. So, asymmetric synthesis has become a very important area in pharmaceutical industry who are making drugs. Okay. So, as I said that if you have a ketone where there is a methyl and a phenyl, I gave you an example of ethyl and methyl. If you reduce with sodium borohydride, you get both R and S, because the transition states leading to the S compound or the transition state leading to the R compound, they have the same energy, and so the activation energy for the two processes are same. So, they will be formed in the similar rate, and ultimately it will be a 50-50 mixture. So, this is a symmetric synthesis, not asymmetric synthesis. On the other hand, if you have an aldehyde, if you have the same ketone, phenyl methyl ketone or acetophenone, that is commonly known as, and if your reducing agent is not chiral, is not borohydride, is a chiral hydride source. That means, it is a boron which was attached to a chiral group here. So, maybe all the hydrogens are not present, maybe because you need only one hydrogen of the boron to reduce the carbonyl to the alcohol. So, maybe you have one boron connected to one hydrogen, and the other groups are basically chiral groups, and in only one chiral configuration. If that is, those are called chiral boron reducing agents. So, if you use that compound, chiral boron reducing agents, then what happens? The transition states, because in the transition states it is the complex, the boron is complex to the carbon. So, that complex will immediately make a chiral, will involve chirality, make the molecules chiral. Okay. And then when the hydrogen comes and produces a new chiral center, they are formed in unequal amounts. Okay. So, actual result is when it is used in, it is not said which chiral boron agent is used, but a chiral hydride. These are hydride transfer agents. Chiral hydride transfer agent is used, and you can get these two alcohols in unequal amounts. So, the experiment that was done here was that S compound was obtained in 97.5% and 2.5% is the R compound. So, now you know what is enantiomeric excess. The enantiomeric excess will be 95. It is the difference between the two. Okay. Enantiomeric excess, again I repeat, it is the enantiomer, percentage of enantiomer in excess of the racemic counterpart. Okay. So, this is the start of the asymmetric reaction. Okay. I have already told you about the selective synthesis. Now, in asymmetric synthesis, there are again two terms. One is enantioselective reaction and the other is diastereoselective reactions. Okay. So, if your products, suppose the products that are obtained, possible products C and D are linked by the enantiomerism, that means C is the mirror image of D, and if you get only C, then that reaction will be enantioselective, because you are getting one enantiomer over the other. If it happens to be that C and D are not mirror images, they are diastereomers, and you get only one in major amount, suppose C is in major amount, then that will be called a diastereoselective reaction. Okay. So, depending upon the relationship of the products, you can call them as enantiospecific or diastereospecific or diastereoselective or enantio. Sometimes specific is also called, but the better term is, because specificity is reserved for the configuration of the starting material. So, it is better that you use this enantioselective and diastereoselective. So, here this is a diastereoselective reaction if you get one diastereomer over the other, and if you get one enantiomer in excess over the other, then that will be called enantiospecific. Okay. Now, remember when we started with the carbonyl chemistry, I said that if you take a flat carbonyl with two adjacent hands and none of the hands are chiral, then what happens? The nucleophile, which is also suppose not chiral, when it comes, then it generates transition states which are enantiomeric in nature, and that is why the rates of formation of both R and S compound will be same and you get 1:1 mixture. However, suppose a molecule already has a group which is chiral, which has got a chiral center in one particular configuration, if you can get it, and suppose this is another group R. So, now this molecule is not chiral here, but overall it is a chiral molecule, because it has got a chiral center somewhere in L. Okay. And suppose this chiral center, whatever is present in L, is having an S configuration. I think better make it another group, say X, in S configuration. Okay. And you now add the nucleophile. Okay. So, the nucleophile will add to it this is one possibility. I am not drawing the three dimensional structure, just a rough sketch. So, this is one possibility, and the other is the nucleophile on this side and OH on the other side. Okay. X and L star remains. Okay. Now, suppose now this is still S, this is still S, because you have not touched the chiral center of L. What you have done is you have created a new chiral center. Okay, you have created a new chiral center. Now, there is a possibility that they will have configuration. Suppose the sequence, I did not know what is the nucleophile, but suppose we have a sequence order here such that this becomes R. So, then this has to be S. Okay, if this is R, then this is S. I am not giving any priority order. Suppose this becomes R, the priorities are such that this carbon becomes R, then this carbon will become S. Okay. So, what is the two products? The two products are SS and SR and SS. What is the relationship between these two products? The relationship between these two products are diastereomers. Okay. And that implies that this is going into the two products, the RS or the SS, because these are diastereomers. So, these two will be also diastereomers, because the transition states, if you take the mirror image of this transition state to the and the other transition state, a mirror image of one transition state, and try to compare with the other transition state, it is not possible, because you have one configuration which is always S. So, taking the mirror image of one one in transition state, you have to make this R, but that is not possible because this is fixed S. So, the transition states now you have will be diastereomeric. That is why I gave different heights. Why these are diastereomeric? Because you have already a prefixed, predefined configuration for which you do not have any mirror image in these transition states. This transition state always have this SL, L as the S, and then if I write it this way, that this will be S, and if the configuration that is being generated is R, then this will be SR and this will be S, but this is relationship is diastereomeric. So, the principle of asymmetric synthesis, as I told you earlier, that you have to go through diastereomeric transition state. So, if you go through that diastereomeric transition state, you will get selectivity, or you will get the asymmetry that you desire. Okay. So, asymmetry can be obtained in various ways. One is the molecule already having a chiral center, that is one way. The other is that you use the reagent which is chiral. Then also, because in the transition state the nucleophile is involved, and if the nucleophile has a particular configuration, so then the configuration is fixed, you cannot have the enantiomeric mirror image, then you have to have diastereomeric mirror image. Okay. So, the other possibility is the nucleophile can be chiral. There is a third possibility that there are, if it is a catalytic reaction, some reactions can be catalyzed, then the catalyst can be chiral. That what happens in biological system, that why natural products are chiral, why all natural products nature makes are chiral, because nature uses enzyme which are chiral catalysts. So, whenever a reaction is done via a chiral catalyst, then also you can get asymmetric induction or asymmetric synthesis, you can achieve asymmetric synthesis. Okay. So, these are the three most important ways. Either you use already a prefixed already an attached asymmetric center, or you can have a chiral nucleophile, or you can have a chiral catalyst, or sometimes what happens that if you do not have any asymmetric center, but what you do, you temporarily attach a chiral center into it. Okay. Temporarily attach a chiral center in it and then do the reaction. Then also the transition states will be diastereomeric because of this chirality of this A. Okay. And then after the reaction, once the asymmetry, degree of asymmetry is achieved, then you can take this A off and get the original target compounds. Okay. So, that is another way. So, if the starting compound is not chiral, you attach some chirality in the molecule and then do the reaction, okay, and get the diastereomeric transition states. Or you can have chiral reagent, as I said, or you can have chiral catalyst. Okay. Sometimes chiral solvents also can induce asymmetry in the reaction. Okay. Now, let us take the cases where there is a carbonyl and the carbonyl is attached to a carbon which is having a chiral center. Okay. So, chiral center means there are 3 groups here and there is a R group here. Now, if you want to do a reaction, say a borohydride reduction or a magnesium or RMGX addition, methyl magnesium bromide addition, then you are passing through a diastereomeric transition state. So, you will get the alcohols. If it is borohydride, a borohydride, then you will get an alcohol. If it is methyl magnesium bromide, then you will get a tertiary alcohol. But the question, the fact is that you are going through a diastereomeric transition state because you have a chiral center here which is fixed. Now, there are certain rules which can tell you which compound is going to be obtained in major amount. So, now let us take this system, inspect what I am saying. I am taking a carbonyl compound, see this is my carbonyl group and there is a group attached, any group I can attach suppose carbonyl in one hand there is a symmetric group, okay, and the other hand there is a attachment of a carbon which is chiral, because this is red, this is white and this is a different group. So, this is a chiral group, chiral center is a carbonyl and carbonyl has other hand. Okay. Now, you are doing a reaction, suppose a borohydride addition onto this carbonyl. So, the borohydride has the possibility the hydride can come from this side or hydride can come from this side. The question is which side you will be preferred. Now, there are certain set of rules to decide upon that. Okay. What are these set of rules? So, that we will discuss now. Okay. The first is, say this is the situation that what I am saying, that you have a carbonyl group, but this the rule is very general. It could be X, could be carbon also. That means, you are adding a nucleophile onto a carbon. That happens in a Michael type addition, C double bond C. Usually nucleophile does not approach, it approaches only when there is another electronegative group further down. So, if it is carbon, that means it is in a Michael type addition, or if it is oxygen, then it is 1,2 carbonyl addition of onto 1,2 carbonyl system, or if it is nitrogen, then it is addition on the imine. Okay. So, whatever I am talking about the carbonyl, the same rule applies for carbon, that means double bond, as well as for the imine. Now, let us see what is the problem. The problem we are defining is that there is a group which has got a chiral center here, stereogenic center, that is the common, that is the modern name. Now, there are these two possibilities, the nucleophile can come from the top or can come from the bottom. And so, these two faces are no longer enantiotopic, they are diastereotopic. Why? Because the products, the way to do it is that the products obtained from these additions are diastereomers. So, the faces are diastereotopics. Okay. Or the other way around, that if there is a chiral center already attached, the faces becomes diastereotopic. Okay. But for easier understanding, you can say that the products that are obtained from it are diastereotopic. So, the faces are diastereomers. So, the faces are diastereotopic. Okay. If they are enantiomers, the products, then the faces are enantiotopic. But the same ray psi concept is still there. That means, if this is 1, if this is 2, if this is 3, then that is 1, 2, 3, that means that goes in a clockwise. So, the top one is the ray and the bottom one is the psi. Okay. So, this is the scenario now. Now, so question is which face will be favored, that was our problem. So, now let us break down this carbonyl, attach the alkyl, the groups attached to this carbon. So, our problem is that we have a carbonyl system where this is R, do not have any chirality here, but the next other hand, the next carbon is a chiral, carbon. So, it has got 3 additional ligands. Now, out of these 3 ligands, one will be, this is now the pure steric, the size, the steric size of these groups. So, one will be small, another will be medium and another will be large. Suppose this is the case, that there are 3 groups. So, one is small, so this is large suppose, and suppose the white is the smallest and the red is the medium one. So, you classify these 3 groups which are attached to the stereogenic center as large, medium and small. Then you try to figure out that what is the preferred conformation of this molecule. See, this is, there is this free rotation happening in this molecule, free rotation. So, as the free rotation is happening, that means it has got different types of conformations. So, which conformation is preferred, and according to Cram, the conformation that is preferred, that will give the measure product, that will react in a particular fashion and that will give the measure product. So, according to Cram, if I go to the board, according to Cram, this is the simplest, the first rule that came out of addition to a carbonyl adjacent to a chiral center. Okay. So, according to Cram, that you have a conformation which is most stable is the one where the carbonyl has another group, that is R, where the next carbon, that means the chiral carbon, the large group is anti to the carbonyl. So, if that be the case, then there will be a small group, suppose on the right side, depending that of course depending upon the chirality of that center, but suppose this is the case that it has got a conformation like this SML, or you can have another SML, okay, or depending on the chirality, again I say that you can have the other one also, R, L, S here or M there, okay. But for a particular compound you will have only one set. I will go through the example. So, the most preferred conformation will be this or this one. Again I repeat, this is that depends on the chirality of the stereogenic center, whether LMS will be anti-clockwise or LMS clockwise, that depends on the configuration of the chiral center. But this is the preferred conformation, where the carbonyl, the other way to say, the carbonyl is flanked between the small and the medium. Okay. So, once it is fixed like that, then the borohydride, suppose I am doing a borohydride reduction. So, boron is complex to the oxygen and then it has got the hydride. So, the hydride will now approach the carbonyl from the side of the smaller group, and it will the hydride could have approached from the side of the medium group, but he says according to Cram that this approach is not favored. The approach which is favored is the hydride or the nucleophile. Here hydride is the nucleophile, that is the that approaches from the side of the smaller group. So, if that happens, that means OH will be on this side and hydrogen will be on this side. Okay. So, let us go to this example which is written here on the slide. Okay. So, this was my compound, and if you try to draw the correct Newman projection, keeping the carbonyl flanked between the small and the medium, you should not make any mistake which side will be S, which side will be M. So, the way to do it now is the carbonyl is actually the front carbon, okay, front carbon. That means, if you look from this side, so you see the LMS is from this side, again I repeat, if you look from this side, the LMS looks clockwise. Okay. So, whenever you put these groups LMS, that should be in a clockwise fashion, LMS, that means you are on the correct path. Okay. Again I repeat, carbonyl is at the top. So, you have put the carbonyl at the top. So, the LMS, while viewing from this side, you maintain that whatever the directionality of LMS. So, that is maintained here, LMS is like that. So, this is the correct conformation of this, and the carbonyl is flanked between S and M. So, according to Cram, now L is anti to the carbonyl. So, now the nucleophile will approach from which side? From the side of the smaller group. Okay. So, that is from the side of the smaller group. So, this will be now according to Bargy-Dunning principle, the hydride should approach at an angle of 107 degrees. So, it will approach in an angle like this, So, it approaches from an angle like this. So, if that happens, then R goes to the right side. So, this is the nucleophile, and this SML remain at the same position. Only when the nucleophile comes from this side, the oxygen goes to the nucleophile comes from this side, the R moves to the right side, which remains at the same position, because it was 107 degree. So, only slight deviation, only slight adjustment this CO bond has to do. So, it is almost at the same position. So, this is OH, this is M, this is S, and this is L, and that is R. So, now you can from the, if the nucleophile approaches from this side, then the R will be on the left side. Okay. So, that is the difference. So, this is the these are the two diastereomers possible, but the major product is the obtained what is when the nucleophile approaches from the side of the small group. So, this is what is called the classic Cram's rule. Incidentally, Donald J. Cram, he gave that rule. He received Nobel Prize later on for some other work, not this stereochemistry work. there are other interpretations, other rules which can also explain the formation of this as the major product, and we will end up with this. This is the other model which is called Felkin-Ann model. In the Felkin-Ann model, they differ from the Cram model in the sense that they say that the preferred conformation is not that the carbonyl is flanked between the small and the medium group. Here they say that the large group has to be perpendicular to the carbonyl. So, the large group has to be perpendicular to the carbonyl. So, this is L then, and then you have to maintain that what I said from this side LMS is clockwise. So, that you maintain LMS is clockwise. So, this is one configuration, but the large group can be on this side also. So, you rotate by 180 degree, bring the large here and the medium here goes there and the small comes here. Now, between these two, which one is here? It is there is RS interaction, where the interaction between R and the S group, the small group, and here it is R and the medium group. So, obviously, this one will be the more stable one. So, now the nucleophile will approach from this side opposite to the L group. So, it will approach from this side and from the side of the small group. That means, according to the Barge-Dunich, so it comes from an angle of this 107 degree, and the product, I do not know, the product is not written here, and the product will be formed. If you have to just put the nucleophile here and the wedge almost at the same position, and R goes in the opposite direction. Okay. So, this is what is called Felkin-Ann model. I think next day we will do this in a more elaborative fashion. So, according to Cram, this is the situation, this is the preferred conformation, this is Cram model, and according to Felkin-Ann model. So, you have to place this, that the carbonyl is this is R, then L is here, M is here and S is there, and not the other way. Other way around means L is on this side, and then what happens? You have interaction between R and medium. So, L, medium and S. So, this interaction will be there. So, that will not be there. So, this is the favored conformation. Now, the nucleophile approaches as per the Barge-Dunich trajectory, and then carbonyl almost stays here. So, the product that will be obtained is, so R will move out now. So, this is OH, this is R, this is the nucleophile, and then you have the S, you have the L and you have the M. So, just slight, you can just move it a little bit to eclipse all these. So, S is somewhere here, okay, somewhere here, M is here and L is there. Okay. So, that means if you rotate it, S will eclipse nucleophile, M will eclipse OH and L will eclipse R. It is the same product, remind you, it is the same product as the Cram product, but this is a better approach than the better approach. Later on, this is supported by quantum mechanical calculations. So, now many people prefer the Felkin-Ann model and not the Cram model. We will discuss some other systems, some of the tricky systems where the Cram had to extend his model, or Felkin also had to extend his model. Earlier model was based on steric size of L, M and S, but later on they found that if one of the groups is a polar group, or if one of the groups can form chelate complex with the carbonyl, then the whole thing falls apart, this model falls apart. So, you have to change the model and accordingly draw the preferred conformation and get the correct product. Okay. So, we will do that in the next class. Thank you.